So thank you for the introduction. And well, so what I'm going to talk about today is about the estimation of the location and velocity vectors associated to one or multiple point targets by means of multistatic FMCW radar. And more specifically, I am going to present a technique which we call grid hopping, which more precisely is more extending strategies which have been developed in other fields than radar, and that we can generalize and then reparticularize to radar applications. So I will start first by introducing the context of the multistatic radar target estimation, although it has already been done somehow by the great keynote we just had. Then I will put a little bit of useful math, hopefully not too much, on about so-called direct and indirect procedure for the estimation using such system. Then I will present the grid hopping technique in a generalized concept before applying it specifically to radar, because we'll see that there are a few challenges about that. And finally, I will show some experimental results that we performed last year to validate the algorithm. Okay, so let's start. So basically, a multistatic radar, as we have already seen before, is composed of one or multiple transmitters, but for sake of simplicity here, we will consider one single transmitter, and multiple receivers which are located remotely and far away from one another, which has the main advantage that we see the target from different angles, and therefore we can have some kind of diversity, because it is unlikely that the scattered pole provide a low power reflection. So another advantage with this configuration with respect to monostatic or just diastatic is that you can estimate the location and velocity vectors completely, and not only the radial speed, for instance. So here, just a few notation to start. So the goal is to estimate the location X and the velocity V of one or possibly multiple targets. But each receiver somehow has only access to a projection of this information, which is the range or the radial speed, which we denote by R and U. So the first strategy, so it's really a class which includes a lot of different possible algorithms. The main possible strategy is indirect methods, where first we apply some well-known algorithm for the to estimate first the range and the speed, and then in a second step we combine all of them to recover the location and speed, for instance with multilateration or triangulation, depending on the kind of sensor we have. Also there is the direct method, which will be the focus today, and in this kind of algorithm, we gather all the received signal and process them jointly to directly estimate the location and the velocity, possibly of multiple targets. Well, the advantage of this method, to be quick, is the robustness, but it also comes with a much higher computational complexity, as we will see just in a few minutes. So basically, the goal of this talk is to show a method to still keep the advantage of the direct procedure while having a computation time which is more similar to the indirect procedure. And to do so, we will leverage a technique about cross-factorization, but also the emphasis will be about the interpolation, which will be used to perform what is called a grid hopping somehow. The interpolation will be used to go from one grid, which is defined in the range domain, to another grid, which is defined in the location domain. Okay, so now a little bit of math, but not too much on the on both methods. So just for a general model, we have the parameter theta, which if you consider a single transmitter receiving pair, we have theta is the range and the speed. And so somehow the received signal, if you consider one single target, is a product between first complex coefficients, which amounts for the attenuation, the phase shift, and so on, which occur during the transmission, and times a waveform, which we call an atom in connection with the sparse coding theory. And when we have multiple targets, simply the signal adds with one another, and so somehow recovering the parameter theta k amounts to find a sparse representation of the signal y in the dictionary defined by the atom function. Now, if we go to the global model of the multistatic radar, we can see it as first the parameter of interest, which will be the location and the velocity. And there is also a parameter which is observed, so theta, as I explained before. So we have kind of a two-step estimation. The first model, which is, so the parameter of interest was projected on an observed domain, and this observed domain is then sent to get the measurements y index 1 to q. So q is the index for the receiver. So basically, the indirect method is a two-step one. So first we estimate theta, and then we gather them to correct the estimate of p. So this is something I explained a few slides before. And more precisely, to perform the first estimation of theta, since the main goal of this talk is to perform the estimation in a fast manner. So we'll focus on OMP, which is known to be very fast. And basically, with this algorithm, as we have already seen in previous presentations, it greedily optimizes the correlation between the received signal and the atom function. Regarding now the direct method, we perform directly the estimation of the parameter of interest p by viewing A of S of p as directly our atom. So we worked on the domain of p instead of the domain of theta as before. And once again, this can be estimated in a OMP-like manner. So by greedily optimizing the following global correlation function, which is a sum of multiple correlation functions. And so just to illustrate, if we now just focus on the estimation of location, we put aside the speed for time. So on the left, you have the correlation function that you would have for the indirect method with the range as the x-axis. And on the right, you have the global correlation function directly in the location domain. But what this implies that if you want to maximize this function, usually due to their high non-convexity, you evaluate it on the grid. But on the first case, you have to discretize a 1D domain. So to get a given density with respect to the radar resolution, you will have a requirement of much less grid bins on the first case than on the second case, since you have to discretize a 2D domain. And so the idea of grid hopping is somehow to estimate the evaluation on the grid on the right from the evaluation that we have on the grid on the left. And the main ingredient to perform that is the interpolation. And so basically, let's assume that we have the L grid bin on the theta grid, for the 1D1, and we take its neighbor to select some interpolant atoms. And so we just interpolate the atoms which are in between the grid bins using some patterns. And so there are many different possible patterns, but for radar atoms, a pattern which is very efficient is the polar interpolation. But I do not have the time to go into the details about how the polar interpolation works. So let's just go on. And basically, if we come back to our main goal, which is to approximate the global correlation function, what we can do is to first perform an offline computation, which hence do not affect the efficiency of the real-time estimation. And so this offline computation first is a computation of a lookup table between an index L in the theta grid toward an index N in the P grid. And what we want to do is that for each index in the grid of the parameter of interest P, we want to associate an index in the grid of the observed parameter theta. And then from this lookup table, we can also compute still offline the interpolation coefficients. And somehow the computation of all the scalar products required for the global correlation function above for the first one in this slide can be approximated. So this amounts to B times Y. So B times Y would be the correlation function for all the value P in the grid PG. Can be approximated as a product of first A times Y, which amounts to the indirect procedure, because A is on the grid theta, and then times a sparse matrix that can be computed offline. And somehow when you do that, you replace your computational complexity of M times NP, and NP is very large. You replace it by M times theta plus NP times I. And it is difficult to know which one of these two terms, the complexity on the right, dominates, because it strongly depends on the choice of interpolation and the density of the grid. So somehow they are the kind of same complexity. And just to illustrate it, so first we compute the correlation on top, which corresponds to the one for the indirect method, and then perform a mapping plus interpolation to get the 3 on the bottom, and then adding up to get the one on the left. And just to see how it performs. So on the left, we have the exact evaluations on the grid PG of the global correlation function. In the middle, you have the one we approximate with grid hopping, and on the right, you have the approximation error. So this is performed with the polar interpolation I just talked about before. So now we can apply it specifically to multistatic radars, because there are still a few subtleties about that. So basically, here I was defining the parameter of interest of the location and velocity. But what we can do instead, is first just estimate the location, because Y, the received signal Y, can be reshaped into a matrix and be reformulated as an outer product of two atoms, R and U. But U depends on both X and V. So we cannot perform a 2D Fourier transform as we did as we would do for monostatic radar. And so basically what we do is that we just concatenate all the matrix of Y1 to YQ, so the Q's receivers, each matrix. And so we will assume that each of the Q times M out columns is a signal. So we will do as if we had Q times M receivers. And then we perform the correlation, which is on the bottom, which can also be solved with grid hopping. And finally, as a second step, we assume that the estimate X that we got is fixed, and then we can approximate the velocity, which can also be performed with grid hopping. So here's an example, just the correlation function obtained with grid hopping, first for the location, then we extract the signal corresponding to this location, and then we perform the correlation for the velocity. But the problem in this situation is that the lookup table for the velocity can no longer be computed offline. You need to compute it online, since it depends on the value of the estimate X you got, because the link between V and U depends on X. So you need to compute this online. Fortunately, due to the linearity of the link between V and U, this can be quickly done in some cases if you have a uniform grid. And if you use a very simple interpolation pattern, you can compute this online. And so finally, we perform experimental results to test the method. So we designed an active multistatic radar with a single transmitting antenna and 8 receiving antennas. But we had exactly 4 different locations and multiple arrays. So for simplicity for now, we just process the data with 1 antenna for remote location, but we could go further. So this is just a picture of the setup. So we had a road and we had some cars going by the road. And just here on the left, you have the range Doppler map from which we can apply grid hopping to get the mapping on the right. And we can also compare it with the one we could have if we did not apply grid hopping, but the direct correlation function, and once again, the error. So this is from measurements, while before it was from simulation. And so here's an example of, in green, you have the real path traveled by the car, and in black, you have the estimates obtained with grid hopping. So finally, here's just the results. So on the left, you have the computation time with respect to the density of the grid of the parameter P. Of course, if you increase the density of this grid, you will have a higher computation time. But you see that the direct method without grid hopping needs a much higher computation time than our method. While the performance, if you look on the right, so the x-axis is it's kind of a tolerance threshold between the estimate and the true value. And so we just counted the number of time we had a hit with respect to this tolerance threshold. And so you can see that whatever you choose for this tolerance threshold, you have that the grid hopping perform very more like the direct method than the indirect method in terms of performance. But for the computation time, it's more like the indirect method. So now for the conclusion. So we showed how the direct method performs better than the indirect method for multistatic radar. We proposed the general framework of grid hopping and then particularize it to the factorization framework of the multistatic radar. We also validated the method with some measurements, experimental validation. And for the perspective, we can extend the model to include into the projection model the angle estimation, which was for now kind of put aside, but we could add it to the model. And also we can extend the algorithm to go off the grid, because this is something we did a few years ago, and so we could combine the two research to use once again interpolation to leave the grid. So thank you for your attention. And if you have any questions.
Yes, thank you, Gilles. So questions from the audience? Do we have any online?
At the moment, but I have a question. So if when you did your real measurement using your setup, did you uncovered like unexpected effects that your model wasn't considering, or was everything going to plan, as to say?
Well, I'm not sure exactly what specifically you mean by unexpected effect, but of course there's a lot of unsaid part of the processing in this presentation. Since, in fact, before applying our algorithm, there is a whole part of pre-processing of the data in order to remove the clutter. And moreover, the one difficulty with our signal is here you see because we have very far away remote location from which we have to make the RF signal come back. We need to have very long signal coax cable, which convey a 24 gigahertz signal. And therefore we need to amplify a lot the signal before. And these additional components can add more non-idealities, and moreover, due to the way of the FMCW radar perform its demodulation, some very small non-idealities on the antenna side can end up with being very strong problems in the receiver side. So this is something we had to deal with. And so for now, we just apply some very aggressive clutter removal, which could be improved in the future. I don't know if it really answers your question.
Any more questions?
So, okay, so I also have then another one. So I think you mentioned that to me that when you were doing the calibration, I think of the when you were doing the chirp, so you had like some issues at the beginning because the chirp was not like properly calibrated. I don't know if you remember that. But then did you consider, because of, in a way, did you consider exploiting that within your model? So the issue was that but when you do FMCW radar, you expect to have like a nice chirp. And so the idea is because the chirp is a proper line, your time delay is translated into like a frequency shift. Okay. But if you don't have that, because for example, what happened is we were maybe a bit too lazy to calibrate and we thought it should be fine. Yeah. But then, so this relationship was not there anymore. And we had like really strange patterns. Did you think about maybe leveraging that in your model to then increase your quality of reconstruction?
Well, it's something which could be used, since in a manner you can see the non-linearity of the chirp as a different way of sampling the signal. It is equivalent to use a non-uniform sampling and having a non-linear chirp. So this is something which could be used to improve the performance, but we did not consider it for now. But well, it is true that actually when you use a monostatic radar and this calibration is not perfectly done, you can still find a way. It's okay. It will not have great consequences. While in a multistatic radar, this is something I just explained before about the long cable, which increase all the non-idealities. And this is also something which happens because of this long cable when we have a slight misalignment between the expected chirp and the exact one. It results in huge problems, which we had to. So we had to stop being lazy and calibrate it perfectly.
So if there
I
any
have
more
one
questions?
last. I have one last one.
Okay.
So, but then, given the, let's say, challenges and difficulties that you encounter using those type of systems, do you think that at some point they will be widely accepted as like a commercial solution?
That's a very good question. In fact, I'm not totally sure about that. I think in the end, it would be more affordable to, or more practical to transmit the RF signal through another antenna, a very directive antenna instead of cables, because it could be cheaper and without the problem I just mentioned. Here in our case, it was easier for us to use these cables since we had more control of what we had to do, and we had less, we have more expertise on this kind of building of setup than using an additional antenna, which could cause actually other kind of problem of calibration. So anyway,